Okay, well, I wasn't, you know, of course, Harry and Robin always come. And so I knew at least I would be able to talk with them. And one of the things I was going to ask them was, you know, I thought if it was only Harry and Robin here, what I would do is I would tell them, tell me what's wrong with the talks you've been listening to that I've been giving for the last 6 months. Because I've been talking about the same topic basically for 6 months now. And Harry and Robin heard me give it a couple times, I talk a couple times at Rutgers, and then they heard it overseas. I think they both heard it in Ghent. And Harry even heard it in, oh, and you heard it, well, anyway. Both of them heard it a couple times over the summer at conferences where I gave this same, talked about the same idea. And I've been talking about a way of trying to improve, well, deal with this p-value problem. So the statisticians are all worried right now about all the misuse of their technology. People are misunderstanding p-values, people are misunderstanding the word significance, and what is the matter, why can't we teach this, why is it, you know, why are so many people doing bad things with statistics? This is nothing new, but it seems to be a particular crisis right now for, I don't know why. I don't know why. Well, why has this come to such a head now?
Is it new? I mean, you've been around a while. I mean,
well, you didn't have people writing editorials in science, in Nature magazine, or Science, or I'm sure you're in psychology, I'm sure you're aware of the...
I was thinking more of social psychology, so
yes.
I'm sure you've heard of the replication crisis.
Yes.
So most people attribute it to misuse of statistical methods.
Right. So were you hearing about this being a crisis 10 years ago? Or, well, you weren't here 10 years ago.
No. When I was an undergrad, though, I learned like frequentist statistics, and I didn't even know there was another school. Like that's the level that we get taught in psych, just as a tool to how to use and not.
Some people think the Bayes is a solution to this problem. Yeah. Some people, you know.
You might hear somebody who has that view.
Yeah. But it's not, it's sort of not been. So anyway, I have my own idea about what is a solution, and I also have some perspectives on the history that I wanted to talk about. And so I've written 2 papers that aren't published. One of them I think I will get published. I need to talk to Harry. I tried to put on researchers.one, I didn't succeed.
okay, we'll talk about it.
Yeah, I did. We can talk about that. How many of you know about Harry and Ryan's website called researchers.one? Yeah, he's got this website. It's like you know, you can publish yourself, but or you can just have it refereed and then publish it somewhere else. It's is that fair? Yeah.
If you were limited to 2 sentences, sure.
So if you come to dinner, he can tell you more about it. So anyway, I tried.
There's no place to eat dinner on this campus.
Well, we'll go over that. So anyway, my 2 papers. The first one is a proposal, and the second one is history. When I first tried to, originally there were 1 paper, but I split them. So what I announced today is that I would talk about the history. But I think I will end up going back and talking about the first one too. But I do the people who've already heard it several times. I'd like part of the conversation for you to tell me what isn't understandable about it and so on. But I want to talk about the history because this p-value thing, it isn't entirely new. We've had parts of it have been with us since the 1830s. And I wanted to talk about some of that. So to start that, I don't have that many slides. Partly I could refer you to the you know, we might come to the point where I say, let's look at these papers, and the papers are online. We could look at the papers together. But here's something I'm going to start with. One of the reasons it's hard to read this old stuff, well, one of the reasons is a lot of it's in other languages, French and German. Another reason is that they don't talk about standard deviations. In the 19th century, instead of standard deviations, there were two more popular measures called the probable error and the modulus. Now, the probable error, some of you may have heard of. If you have a normal distribution, I don't know if this is usable, or if this is
The
usable.
blackboard is,
Blackboard is not?
it is, you can write on
It
it.
is. So people were usually thinking about in the 19th century, they were thinking about the normal distribution. And we know that two standard deviations leaves 5% outside and 95% inside. But what if you wanted 50%? Then this distance would be the probable error. So the probable error is the amount by which it's equally probable that you be that close or farther. And that was probably the majority of scientists in the 19th century, and even in maybe the 20th century, because that's still widely used, I think, in chemistry and in physics and engineering. People might talk about probable errors. And there were really two, coming out of the early 19th century, there were two major schools of probability. One we could call Laplacian, after Laplace, the other Gaussian, after Gauss. And certainly everybody who had studied Gauss and was using least squares in astronomy or geodesy or engineering or physics, they would use the probable error. They would just say, okay, the answer is 52 plus or minus, or 52.3 plus or minus 1.2. And the plus or minus was not two standard deviations, it was one probable error. So it didn't mean you were sure that that was the interval, you were giving a 50% interval. With 50% probability, it should be 50.1 plus or minus 1.2, or whatever the plus or minus said. So when you see plus or minus, it means probable error. And I suppose that in some sciences, that's still the way it's written. The probable error is what people use.
Is this the width of a 50% confidence interval
Yeah.
in today's term? Okay.
Yeah, so they gave a 50% confidence interval,
Half width of a 50%.
half width. The probable error,
Oh, okay.
yeah, it's the half width of a 50% confidence interval. Now the Gaussian and there was a big difference between the way the Laplacians and the Gaussians looked at things. And you know, I don't want to exaggerate too much. People didn't call themselves Laplacian or Gaussian. But still there were two traditions. If you picked up a book about probability in the middle of the 19th century, or even any time in the 19th century, you could tell which it was. The Gaussian books emphasized least squares, and they never told you how big a confidence interval you needed to be sure. It wasn't about being sure. It was about getting the best estimate. So if you're a surveyor, if you're doing surveying, or even if you're doing artillery, if you're doing artillery, you don't have time to talk. If you're trying to shoot the enemy, you don't have time to talk about what is the 95% confidence interval from where he is. You want to know, where am I going to shoot? You want one estimate. That's it. If you are doing a survey, surveyors, I don't know if you ever dealt with surveyors. I was once involved in a land dispute. Surveyors, they're not paid to say, maybe it's here or maybe it's here. They say, this is where it is. Put a stake in the ground. They want the best estimate, right? So in geodesy, you know, like people put, you know, and this geodesy was important in warfare. It was important in drawing boundaries between countries, and Laplace was in charge for a while of that kind of an operation. And at the time Laplace was in charge, it was the best in the world. The French were the best geodesists. You know, measure the stars, measure the land, everything. They were the best. But by a few decades after Laplace's death, it was clear that the Germans had it right, that the French couldn't get. The French were impossible. What was the problem? Well, part of the problem was that after the monarchy came back in France, people weren't interested in scientific research anymore, and they said, oh, we just use the methods we've been using, we want to improve them. Whereas the Germans were improving them. That's part of the story. Another part of the story is that the French were depending on the law of large numbers in the central limit theorem. And all you need to do to be more sure is to take more observations. And the Germans were saying, we don't believe that stuff. We think they're systematic errors. What we need to do is improve the instruments and improve the calculations and so on. So they were paying much more attention to those details. And you know, by the 1840s, all of Europe realized we've got to use the German methods. The French don't know what they're doing anymore. So that if you look at the books on least squares by the Gaussian school, you don't see anything about confidence intervals. All you see is about what are we going to do to get the best estimate. That's what it's all about. Whereas the Laplacian books, what are the Laplacian books doing? The Laplacian books are interested in medicine. They're interested in social science, studying demography and things like that. And they want to know, how can we be sure? How big of a confidence interval do we need to be sure? So they were interested in practical certainty. Yes?
So your example of shooting someone, and that you wanted to estimate where's the best place to point your gun. If it turned out that there was a certain place that was the best, but there were other places which were almost as good, but there are innocent bystanders there, it seems to me that would be rather important. And so you'd be quite interested in the confidence interval.
I'm just trying to tell the history.
Right. But that's what I would say to one of these Germans. I would try to say it in French.
Okay.
You were saying it with some approval. That's
Okay. Okay. So they had this probable error, but there was another measure they also used. That the Laplacian school did not. At the beginning, the Laplacian school did not use the probable error. They used what was later called, they didn't have a name for it usually, but George Bedell Airy, who was an astronomer, and you could call him in the Gaussian school. He was English, but he was in the Gaussian school. He wrote perhaps one of the first sort of 1861, he published what was probably the first Gaussian manual in English. And he made a table of these different measures, and he introduced the word modulus. So modulus is what Laplace used, and Laplace's followers all used modulus, but they didn't give this name to it. So Airy introduced the name modulus for it, and that was continued to be used for, some people continued to use it for a half a century maybe. But it's the word I'm using because I need a word, and it's the only kind of word that was ever sort of standardized. What is a modulus? Well, the problem with the standard deviation or the standard error, I know some of our people are philosophers. Does everybody know the difference between a standard deviation and a standard error? What does that mean to you, standard deviation or standard error? So does that mean any difference to you?
I'm not familiar with standard error.
Standard error. So this was a word. So standard deviation was a name. The idea standard deviation was around from the beginning. But the name standard deviation was introduced by Carl Pearson. Just to get our terminology straight, standard error. So standard deviation is like, I think, 1896 by Pierce, by 1890s, by Carl Pearson, who's the big leader of English biometry. And Carl Pearson's assistant, George Udney Ewell, introduced a variation called the standard error in 1896, I think. I may not have this right, but I think it's about 1892. So what's the standard error? The standard error is the standard deviation of an estimate. So if you have n observations, x1 up to xn, and the standard deviation for each one of them is sigma, then your estimate of the mean is x bar, which is equal to the average, the sum of the x's divided by n. Its standard deviation is sigma over the square root of n. So Ewell had problems telling these two apart, or talking about them. So he said, I want to give a different name to this one. So the standard deviation for my estimate, I will call whatever my estimate is, whether I'm estimating this or that or the other thing, is always going to have a standard deviation. I'm going to call the standard deviation of the estimate the standard error. Because I'm estimating something and I'm making an error, this is the standard error. So standard deviation means standard error means standard deviation, but it's in a particular context. So sometimes I will say, so this is a kind of a term in applied math. In a kind of introductory textbook, you may never see the term. But a lot of people doing applied statistics still will say standard error. I think it's still used, you still see it. Maybe not as much as you used to. So the point is, what is the standard error? The standard error was called here, Airy called it the error of mean squared. This is the standard deviation or the standard error. And what this says is that the modulus is the square root of 2 times the standard error. 1.414, this is the square root of 2. So the modulus equals the square root of 2 times sigma. That's what the modulus is. Why would you use that? Why would you, instead of using the standard deviation, why would you use the square root of 2 times the standard deviation? Well, the answer is, if you do that, and you write down what is the standard normal distribution? F of x equals 1 over the square root of 2 pi. Well, what is this normal distribution? Normal distribution with mean 0 is, its density is 1 over sigma times the square root of 2 pi e to the minus x squared over 2 sigma squared. Why put that 2 there? Why do you want a 2? What a messy thing. It'd be better, why don't you take the 2 out and put something like c squared here. And then you'd get rid of this 2 too, I think, or something. You'd get what would you get? You get it, I forget what you get. I think you get a 2 up here. Anyway, I'm sure, the constant escapes me at the moment, but you get this expression. You just have x over c squared instead of x over 2 sigma squared. C would then be the modulus. So if you're looking at the formula for the normal density, it's much more natural to use the modulus than to use the standard deviation. And that's where these guys were coming from. So all these 19th century books in the Laplacian tradition, 19th century books and articles are going to use the modulus instead of the standard deviation. So everything is off by the square root of 2. Okay. Now in Airy's table, he also gave the mean error. What is that? that is the expected value of the absolute value of x. So this is the absolute, this is the absolute. So this is not really important. They didn't use this much, but they did call it the mean error. But they did use the error of mean squared, because it comes up in natural ways, and they used the modulus, and they used the probable error. And so Aaron made this table, and this table is just copied from his book. He made this, and it's not, maybe it can be improved, but I didn't try to improve it because it's the way he did it. So what do you see when you see from this book? You see that a modulus is about 2 probable errors. Easy enough. You see that 2 moduli is equal to twice this number. You know, twice the square root of 2 is about 2.8. So 2 moduli is about 2.8 standard errors. And I'll come back to that because of Gavaret. 2 standard errors is about the same thing as 2 standard errors is our kind of 95% confidence interval. So there's a 5% error. But it's also about the same as 3 probable errors. 2 standard deviations is about the same as 3 probable errors. So nobody talked about 2 standard deviations, but you do find people talk about 3 probable errors. So that's the same thing. So when you come to the 20th century and you see R.A. Fisher talking about 2 standard deviations, you know, a lot of our statisticians who do a little bit of history say, oh, that seems to be, R.A. Fisher seems to have invented that. Well, not really. It was very old. It was 3 probable errors. Except Ewell had started talking about, Ewell had started putting, in 1911, before Fisher published anything, when Fisher was just graduating from university, and he was 21 years old, he hadn't published anything, Ewell published a textbook on statistics in which he didn't, instead of using probable error, he used standard error. So by the time Fisher came along, standard error had suddenly become the standard. So Fisher wasn't inventing anything when he said 2 standard errors. It's just that people had changed from probable error to standard error. And they had been saying 3 probable errors, and now it was 2 standard errors. So it was nothing original. 5% was not original with Fisher, in the sense that they were already using 3 probable errors. But then you can also see if you double that, if you double 2 standard errors, you get 4 standard errors. 4 standard errors is the same as 6 probable errors, and since a modulus is 2 probable errors, 6 probable errors is 3 moduli. 3 moduli was the criterion for practical certainty going back to Fourier in 1826. So the question is, in this Laplacian tradition, what did people regard as practical certainty? Well, if you go back, there's sort of course, there's what you consider, when you're doing theory, you know, you make a pretty high standard. So when Fourier was doing theory, he said, if you really want to be sure, you should have 3 moduli. That'll give you only a 1 in 50,000 chance of error. Now actually, he said, he wasn't quite that exigent. He actually said 2.87 is good enough. 2.87 moduli will give you 1 in 20,000. But he didn't think this was very precise, so he rounded 2.87 to 3. So sometimes you see 2.87, that's 21 in 20,000, and sometimes you see 3, that's 1 in 50,000. What's the difference? You know, that wasn't, they weren't considering that difference to be such an important thing, because this is all you know, mushy anyway. But anyway, that's good enough to be sure. Now, when you get to something practical, you got to lower your standards. You never get that much data. So what kind of lowering of standards do you see? Well, one interesting lowering of standards is Gavaret in the 1830s. Gavaret published the first book on medical statistics. So he published a basically a textbook to show people how to use Laplace's theory to tell which of two treatments is better. There were big controversies going on. One of the big controversies was gallbladder. It's the same thing. We still got the same issues. What's the best? Do you have to go in surgically, or can you put a tube in and break up the gallstones? Gallstones is what called gallstones. So there was a gallstone controversy in the 1830s, and there was some data on it. That Dr. So-and-so had introduced his new gallstone treatment, and did it do better than the other treatment people have been using? And so Gavaret, there was a big debate in 1835 in the Academy of Sciences. There was a big debate between the people that said you can use probability to study medicine, and people who said it doesn't make any sense. A big debate between the two sides. And Gavaret saw this debate, and so he wrote a book about it. He said, here's how you do it. But what was his standard of practical certainty was two moduli. If you figure out what two moduli is, 2.8 standard errors, that's about 1/2%. 1/2%. And Gavaret said, my authority is Poisson. Poisson was another big mathematician who was kind of the biggest mathematician after Laplace. I wrote another book on probability. And Poisson said, to be practically certain, you need 4 or 5 or 6 moduli. But when he came to actually doing data, he would use 2 moduli. So Gavaret said, 2 moduli is enough for practical certainty. But, there's sort of when you can be certain, and there's when you think probably. You can't always get that many. Sometimes you say, here's an indication. So what do we see next? Well, first of all, okay. So I call to your attention my working paper number 55, this website probabilityandfinance.com that my co-author Bofk and I have been maintaining. We now have 55 working papers there, and the 55th one is what I'm taking this material from. This is just copied from that working paper. So you can look there and you can see that I'm quoting 24 people, different people during this historical period, so that you can see from their own words what they said. And now I come to Edgeworth. Now Edgeworth was introducing these ideas to the English in 1885. Okay, they're already in Laplace's book in French, they're in Poisson's book, they're in Cournot's book, they're in, there's a German named Lexus, who had, in the Laplacian tradition, not in the Gaussian tradition, German, he's a demographer, he's a social scientist, and he's a professor of statistics. Where was Lexus? Strasbourg. Professor of statistics in Strasbourg, but that's part of Germany then. In the 1870s, they took it over. So Edgeworth reads Lexus's German textbook. Now, why did he have to do that? Well, there actually were books in English, but Lexus was self-taught as a mathematician. Excuse me, Edgeworth. This Englishman, Edgeworth, who was a professor of economics in England, very prominent, self-taught. His aunt was a famous novelist. I think he really depended on, he lived off of his aunt's money. His aunt, what's her first name? Edgeworth. Maria Edgeworth was a famous novelist. He grew up in that family. He was very artistic, very cultured. He studied classics. He didn't study math at university, he studied classics. After that, he got interested in math. He taught himself math. He was a classicist, so of course his German was very good. So when he came to study, the Germans were supposed to be the latest in everything, so he didn't read it by going back to the French, he read it by reading Lexus. And Lexus used 3 moduli, just like Fourier and Cournot. He used 3 moduli. So Edgeworth read Lexis, and he reported it to the English. In 1885, there was a Jubilee meeting of the Royal Statistical Society in London, and Lexis came in. Lexis gave a talk paper at that meeting. Everybody gave papers, and Edgeworth gave a paper about the methods of statistics. And he just taught these elementary things. It was like the English didn't know this stuff. They hadn't been doing it. These were statisticians. Statisticians didn't use probability. Statisticians in England or the United States in 1885 were all economists. Who else would collect statistics? You got statistics on people, you got statistics on how much coal is sold, you got statistics on how much wheat is sold, you got statistics on income, whatever. You got statistics, that's the, numbers about the country, about the economy, about the state. So that's what the statisticians were doing. They weren't doing probability theory. So Lexis said, Lexis had been studying this stuff. He said, I'm going to report to you the methods for probability theory. And so he explained to them how to test for the difference between two proportions, or between two averages. He said, how do you do that? How far is the difference between the average and the results? How can you tell when you have chance, how can you tell whether it's a significant difference indicative of the working of a law other than chance or merely accidental? This was the introduction of the word significant into statistics in English. This is where the word significant comes from. He says, is it significant, signifying, indicative of a real difference, or is it accidental, meaning just random? And he said, he gave an example, and he said, if it differs by twice, or even a fortiori thrice the modulus, if it's 3 times the modulus, then it is exceedingly improbable that that will be by accident. And then he gives examples, and in every one of his examples, he says, he finds out that the difference is more than 3 times, thrice, the modulus, so it therefore is significant, comes by cause. So you go through his paper, every time he uses the word significant, it means, he says something is significant, definitely significant, it means it's 3 times the modulus or more. So for him, significant meant practically certain that it's not accidental. Well, I take that back. Significant does not mean practically significant. Significant means not accidental. So how do you use the word? So to use the word properly in Edgeworth's sense, you say that something is definitely significant, certainly significant, or maybe significant, or definitely not significant. You don't say that something is almost significant. No. Significant is not a matter of degree. The question is, how sure are you that it's significant, or that it's not significant? Significant means signifying a real difference. It does or it doesn't. It signifies a real difference, or it doesn't signify a real difference. So he would say, if it's like 1.5 modulus or 2 moduli, he would say it's probably significant. If it's 3, he would say it's definitely significant, or it's certainly significant. If it's less than 1 modulus, he would say, well, it's really not significant, because even if there is a real difference, this is not signifying it. Right? So significance is not a matter of degree. And Pearson, the great leader of English statistics, adopted Edgeworth's way of talking. And it's a great puzzle to me whether Edgeworth's way of talking was just Edgeworth, or whether it was the way educated, cultured Brits talked at that time. I don't know. I get the feeling from reading a lot of examples that the Americans never quite understood it. And also, that after 20 years or so, by 1920, the Brits couldn't keep it straight either. Because what does significant mean to you? To me, significant just means important. Significant doesn't mean signifying to me. Well, if you say that was significant, okay, maybe it means that it indicates something. I guess it kind of means that, but mostly significant just means important. I wouldn't pick this idea up. And the fact is that Pearson couldn't make it stick. But Pearson, it seemed to be fine with Pearson because in the first 20 years of Biometrica, Pearson started this journal named Biometrica in 1900 because the other journals wouldn't publish his papers. So he started his own journal. And he ran that journal until the 30s. But for the first 20 years of that journal, you see significant is basically used the way Pearson would use it, the way Edgeworth would use it. So in 1912, Pearson says the difference is more than 3 times the probable error and likely to be significant. 3 probable errors, that's 5%. So he didn't, so nowadays we would say, oh, 5%, it is significant. No, he said it's likely to be significant if it's 3 probable errors. But if it's 3 moduli or 6 probable errors, it might be definitely significant. If it's less than 1.5 or 3 probable errors, it's not definitely significant. All right, so anyway, the word significant got degraded. That's one of the, and that's part of the source of the confusion of what we mean by significant now. It wasn't, this is where the word came from, and it is a confusing word, I grant that. Here's an American, Pearl, Raymond Pearl. Raymond Pearl was one of the Americans that went to study with, he went to study with Pearson in London, and became a biometrician, and came back and started teaching statistics at Johns Hopkins. So people in biostatistics know that Johns Hopkins has the oldest and probably still most prominent department of biostatistics in the country. And Pearl was one of the pioneers of that department. And in 1923, he wrote a book for his fellow biometricians about how to do it, a textbook. And he tried to report on, and here he says, he kind of is using the Pearson Edgeworth vocabulary. If it's less than 2 probable errors, it's probably not significant. That's pretty weak, 2 probable errors. That's not 5%, only 2 probable errors. If it's 3 or more probable errors, that means 5% or less, it is either certainly or almost certainly significant. Well, Pearson didn't say that 3 probable errors was not. You needed more than 3 probable errors to be definitely significant in Edgeworth's story. But by the time of Pearl, 1923, it's got weaker. And then, if you read, Fisher wrote his book, Statistics for Research Workers, in 1925. And by then, in 1925, he's using significant just to say, okay, we call anything more than 2 standard deviations significant. And that means that we should look at it again. It doesn't mean that it definitely signifies. Whereas for Edgeworth, significant would mean it signifies. It better be 3 moduli, something big. But then Fisher was just using the word significant to mean 2 standard deviations. We should look at it again. It looks like probably there's something going on, very weak. So this word significant got watered down. Maybe Fisher was not part of the social class of Edgeworth and Pearson, I don't know. Or maybe he had been working for 5, already when he wrote his book in 1925, he had already been working for 5 years at the Rothamsted Experiment Station with people who got their hands dirty. doing agricultural experiments, and maybe they talk this way. Maybe he picked that up from them, this, looser way of talking. Anyway, that's a history of the word significant. So let me back up a little bit, and this is going back to 1816 and 1826. So Bessel, this guy Bessel, what was his first name? Bessel. Anyway, Bessel was a German disciple of Gauss, and 1816 is very early. Gauss and Laplace are doing their things in like 1810, 1812. So already in 1816, Bessel is working very hard to improve the Gaussian, make the Gaussian calculations doable. And Bessel introduced the term probable error in German. So everybody later said, this is not a very good name, probable error. This is Bessel's fault. But it's established what to use it. Bessel introduced the term probable error, and he measured things at probable errors. So he said, what is the odds that you're within one probable error? 50-50, 1-to-1. What's the odds that you're within two probable errors? 1.46. Or rather, the odds are 4.6 to, well, the odds that you're within two probable errors are 1 to 4.6, which means the probability of being outside it would be 1 over 5.6. That would be the probability, the error probability, that you're outside of two probable errors. Three probable errors, the probability that you're outside of three probable errors is 1 in 31. Well, it's supposed to be close to 5%, I guess it is. He stopped with 4 probable errors, which gives a error probability of less than 1%. So this is the table that Bessel gave in 1816. This is the table. These are the first tables that I know of. I think they are the first tables of the normal distribution. And this one was 1826. This is Fourier. So Fourier is a Frenchman. He is in the Laplacian tradition, although he's probably a more brilliant mathematician than Laplace. Fourier is known for Fourier series, Fourier transform, which really comes from his study of heat, the heat equation. And it was probably Fourier's work on the heat equation that inspired, that gave Laplace the idea of how to get the central limit there. Fourier was a mathematician of his time. He was also an administrator and a revolutionary. Laplace, was very cautious. He managed to ride along with all the changes of regime during the French Revolution and everything. He was always on top. Fourier was out there and in waving the flag in the revolution and getting involved, and he almost got guillotined when his side, it's like if Robespierre had not fallen and gotten guillotined himself, Fourier would have been guillotined the next day. That's how much he was involved in the revolution. And then when Napoleon came along, Napoleon discovered how bright he was, and Napoleon took him to Egypt on his expedition and put him in charge of the scientific expedition in Egypt. And then after Napoleon took over the French state and made himself emperor, he made Fourier an administrator. Fourier had to, he said, here Fourier, you got to run this department. A département in France is a region of the government, a region of the country that's run by the representative of the central government in each département, in each region, and he was in charge in Lyon or somewhere I forget where. Anyway, he was under Napoleon, he was a préfet. When Napoleon fell and the king came back, Fourier was in big trouble. Fourier, there was no way, Napoleon had promised him a pension. He was out of a job. He didn't get his pension. But he had a student who was very appreciative of him, who was a royalist, who saved him and gave him a job. And the job was being a statistician. So he was in charge of the census in the Paris region. And he had to prepare the reports, edit the reports for the census in the Paris region. And so he did that, and four big volumes, 1821, 23, 26, and 29. And in the last two volumes, 26 and 29, he put mathematical memoirs, articles in those two volumes to explain how to use Laplace's theory. I mean, for him, this was just he wasn't discovering anything new. He was just writing it up. Here's how you do it. He got most of his time, he was free most of his time to do his own research. But this was like his job, like professors have to teach, even though they mostly want to do their research. He got that job for the last 10 years of his life. He was able to do his research because he had this job as a statistician. And so in his memoir in 1826, he explained to people how to test the difference between two averages. And this is how many moduli, and this is the probability of being wrong. If we divide the number of moduli by the square root of 2, we get the number of standard deviations. I added this to his table. This was his table. This was his table. This is what half of a modulus is the probable error. So if you go half of a modulus, if that's your confidence interval, you're 50%, you got a 50% chance of being wrong. If you want a 5% chance of being wrong, you need to go 1.38 moduli, or 1.39. That is 2 standard deviations. If you want to have a half of 1% of being wrong, you need 2 moduli. We already talked about that. 1 in 20,000 chance of being wrong, you need 2.87 moduli. And Fourier said that's enough. That's practically certain. Now the interesting thing, so this, of course, the 1 in 20, the 5%, that's our familiar 1.96 standard deviations. But he expressed it in terms of moduli. Now, I put these two tables side by side to show you the difference between them. Because it's clear Bessel is going in a different direction than Fourier is going. Bessel is saying, if your estimate turns out to be, if your estimate of a difference turns out to be, 2 probable errors, these are the odds. Whereas Fourier is clearly thinking in terms of starting with the error probability. That's the round number. And seeing how many moduli you need. How many observations do you need? That's just a different way. So this is kind of an entree into understanding the difference between the Gaussian school and the Laplacian school. The Laplacian school is ultimately looking for practical certainty. That's not on the agenda of the Gaussian school. They may tell the odds, but these are the odds that they're, when they finally get their best estimate, you can tell what the odds are for, it being right. But that's not the goal. The goal is whatever it is the best estimate, that's what you got. That's where you are. Whereas so that's an interesting difference. So this is my, so I carried on we didn't get started because we had to set this up. But this is my talk about the history, my working paper. Of course, I'm interested in feedback on it. And it's, it's gotten very long because I quote all these people. 2/3 of it is quotations from all these folks, and it's going to get longer because I'm adding more quotations. So I really look at what was really original about what Fisher did and what was not original. And my conclusion is, what was original about what Fisher did in 1925? The 5% was not original. Saying that the 5% is sort of only, is not, you're not, you know, when there's a 5% probability of error, that's not an indication that you're sure, but it's something you should look at. That was not original. In the Gaussian tradition, one of Gaussian's students, well, Gauss himself said, maybe, you know, maybe these individual errors are the product of many small influences. And maybe the central limit theorem applies, and maybe the individual errors are normally distributed. So within the Gaussian tradition, there was this idea maybe the individual errors themselves are normally distributed. But in the Laplacian tradition, which is what Carl Pearson and the other statisticians were working in, nobody assumed the individual errors were normally distributed. Except Fisher's friend student, Gossett, made that assumption. And Fisher picked that assumption up, not maybe so much because he really believed it, but because he could do the math. He could do the math, starting with the assumption the individual errors were normally distributed, and find out what the distribution of the estimated correlation coefficient was, or what the distribution of the regression coefficient was, and so on. So, or all kinds of stuff. He was very clever at that. He was a better mathematician in that way than Pearson had been. So he proved that he was a superior mathematician by getting all these distributions that were not normally distributed. And if you want to have a confidence interval with these non-normal distributions, you can't just use two probable errors. That doesn't tell you 5%. So you've got to make tables for 5%. So in a sense, what Fisher's originality was that he switched from saying 2 standard deviations to saying 5%. Because if it's a t-distribution, or if it's a distribution of the correlation coefficient, or if it's a distribution of what we now call the f-statistic or something, it's not 2 standard errors. It's not 2 standard deviations or 3 probable errors. You gotta look at the table and see what it is. So Fisher's famous book for research methods for, what do you call it, statistical methods for research workers. I don't know if it was really for research workers. It was to prove how smart he was. It's really a book full of tables. That's what it was. But it was very popular among theoreticians because it was a set of new ideas and it was sort of new math, and the old people that did Pearson stuff weren't smart enough to do it, and so that was where Fisher's originality was. So a lot of why did I first want to write this paper? I first wanted to write this paper because I wanted to point out and emphasize that people were doing this significance testing under different names in the 1830s. And in the 1820s, Fourier was doing it. He applies this to his tables. What is the average age, what's the average age of parents, father and mother, for the firstborn son? He estimated that for the different regions of France. He was interested in how long a generation is. From father to firstborn son, that's a generation. How long on average is a generation? He estimated that and got confidence intervals for it. And then Poisson applied his confidence intervals to look at the test for the difference between birth rates. Well, people were very interested in the birth ratio. Laplace was already doing this. You know, there are more boys than girls born, we know that. Is the ratio the same in Paris and in the countryside? No. Is the ratio the same for legitimate and illegitimate children in France? No. Is the ratio the same for this group and that group? Yes. Is it the same for this group and no? So they were doing all kinds of tests like that. It was a game. And
is that right? That it's not the same for people inside Paris and outside Paris?
Yeah. That's right.
Why is that?
Well, that was discussed a lot. That was discussed a lot. That was discussed a lot. There was also this, not the same for
The usual
legit.
explanation that you read in a is one which looks like it wouldn't make any difference whether you're in Paris. Had to do with the size of the sperm.
Well, there were so many illegitimate children born in Paris that if they all survived, there would be no families that were with legitimate lines after 3 generations.
But how would that make a difference?
There were a lot of illegitimate children in Paris. It appears, here I'm speculating, it appears that children were more likely to become legitimate if they were sons.
I thought it was whether more males than females are being born, not whether they're legitimate.
So if sons are more likely to be legitimized, and if the rate of illegitimacy is greater in Paris, you can deduce that some ratios would change.
It's not the ratio of who's born, but it's the ratio of who's around to get the statistics about.
So we could go through the details.
Sorry, I didn't mean to interrupt. There's just arresting to hear you say no to the 2 things you said no to.
So, so this would all be speculation, but you can spin out explanations along the lines I was suggesting. My hero, Cournot, in 1843, in his book, has a long screed, which I quote in my paper and translate into English, about p-hacking. He says Poisson, he waited till Poisson was dead to publish his book. Poisson was the big, after Laplace died, Poisson was the big cheese in French mathematics. If you were going to get a job teaching math in France, and I mean in the university, anywhere in the country, even in the lycées, Poisson decided who got the job. Poisson decided which mathematicians got promoted. Poisson was not, that was his job. He was, the mathematics, this was a time of, well, this was the time when the monarchy was back. And the monarchy did not like math. But they had to have somebody tell them when the university needed to hire a mathematician, the people in charge needed somebody to tell them who to hire, and that happened to be Poisson. So Poisson was probably the best mathematician of the time. Well, maybe Cauchy was, anyway. Poisson was the most powerful mathematician of the time, even though, the powers that be didn't really like his politics. They had to use him, so he was very... So Cournot waited for Poisson to die, and then he said, all this p-hacking that Poisson did, and then that all these other statisticians have been doing, doesn't make any sense. Because, it may be true that you're only going to be wrong, very seldom wrong if you do one test, but if you're doing umpteen tests, trying out everything you can think of, you may know what you're doing, but when you only show the public the one that looks significant, he didn't use the word significant, he said the one that looks remarkable and looks like it deserves being called to the attention of the public, nobody else can tell how much search you did for that, so it doesn't mean anything to them. It might mean something to the guy that did to the statistician who did it, but not to the public. So this is the first criticism of p-hacking. And of course, it was not the only thing to criticize. Part of what my paper references is the fact that there were a lot of other criticisms. I mean, these things that Poisson and Fourier were doing could also be criticized because they were assuming independence. All these guys, the age at which you get married and have kids independent of your brothers. That's what he was assuming. All these things, there's independence questions about all these statistics they were using from the census. Yeah.
So this result that bothered me, that was found to be significant, might have been just a result of p-hacking.
It might have, but it was actually, it might have. Some were results of, certainly by the time you got down to all the details, there were results of p-hacking. I will say there was in 1830, the French Academy of Sciences, which was when the monarchists were back, the French Academy of Sciences commissioned a guy named Guéry, Michel-André Guéry, to do a study of the census of the whole country. Because one of the things the French Revolution did was that it made France the leader in statistics, collection of statistics. Because one of the first things the revolution did was that they told everybody that they had to register births, marriage, and deaths with the mayor, not with the priest. And the mayor had to report them to the central government. So that was the first country in the world where you had all these, a central government collecting statistics on marriages, births, and deaths, and divorces. The first country in the world where that was being done, and in a country that had tens of millions of people.
Presumably the Catholic Church didn't collect statistics about divorces.
Well, nobody had been putting them together. The parish had recorded them, but they hadn't reported them to the Pope. So it was a centralized collection. And when the monarchists came back, this is what happens, the monarchists came back, the conservatives came back. But they didn't give up the power of all these statistics that were being collected. They started collecting more. They said, we also need statistics on crime. So they collected all the statistics on crime. So by 1830, the French government had this immense trove of statistics, so they needed to have a report on what is going on. So Guéry produced a wonderful, beautiful report on statistics and from the statistics of France, on what he called the moral statistics of France, by which he meant crimes. And Guéry was an opponent of probability in statistics. He was one of the many people that said this stuff that, this was before Cournot wrote his book, but he was saying this stuff that Poisson and Laplace did is pure nonsense. We don't need any probability to understand. We're collecting statistics from 20, 30 million people. We don't need any probability theory. We can look and see what's going on. We can look and see, and we can see that the closer you get to Paris, the less murders there are and the more suicides. Just look, there it is. He drew nice pictures with colored pictures, maps of France showing what happened. He said, you can also look and see, he collected all kinds of crimes. He says, it turns out that in murders of passion, the husband is far more likely to murder the lover, but the wife is far more likely to murder the husband. So that was one of the things, he's got all kinds of statistics like that, and he didn't need any probability theory. What is that to the side? I love this stuff, this history. So the reason I got into this, though, was I wanted to talk about the fact that when we talk about the folks now that are complaining about p-hacking, that are complaining about significance tests, that are complaining about the way we aren't teaching statistics effectively, like to blame it on Fisher and Neyman and so on. And so my point was, this stuff was going on, 100 years before Fisher and Neyman. You're going to have if there's this p-hacking problem, the problem goes deeper, and you're not going to solve it by getting rid of the word significance, which didn't come until 1885 with Edgeworth and Pearson. You're not going to get rid of it. We need to do something more deeper to get rid of it. And of course, that brings me back to the talks I gave last spring in this seminar about my proposal for improving the situation with p-hacking and with errors in statistical testing. And that proposal is to replace p-values with bets. To be more precise, replace p-values with betting scores. So I wanted to use part of the seminar and to return to that and ask the people who've heard my talk 3 times already about that for feedback about what they didn't understand about it, or what they didn't, wasn't convincing, or what I should do better. And mainly that's, were you raising your hand to that?
Yeah, well, before you move on to that, you did mention in the abstract, you mentioned briefly here, but you did specifically mention this paper of retiring statistical significance. And I saw you mention it in your paper too.
Yeah.
I know what you just said, but I mean, do you have anything more to say on this?
I was kind of surprised. How many of you saw that commentary in Nature magazine, the journal Nature, which of course, like Nature and Science being the 2 most prestigious. In March, there was I don't know if everybody knows about this. In March, there was a kind of editorial, you call it commentary, published by Nature, and with 3 statisticians as authors, but endorsed by 854 statisticians.
I don't
Yeah.
even know if any of the authors were statisticians, but
Gelman
all
did.
800 of the people weren't all statisticians. Gelman wasn't an author on the paper.
Oh, wasn't he one of the 3?
I don't think
Who were the 3
so.
authors?
It's like one of the.
Greenland.
Greenland.
The leading one is a professor of business.
One's in business and one's in zoology.
Right. Well, Greenland was one of them.
Greenland.
Yeah.
But
So-
Gelman was one of the endorsers.
Yeah, but yeah.
So I was surprised. Well, you know, I had a conversation after the last seminar here. I think Deborah Mayo was here or something. On the train back, she told me about refusing to sign it. And the whole idea that you're going to, you know, decide how to do science because people sign petitions is, you know, a little bit up for discussion. What surprised me about that, about what they wrote, was how much they were complaining about people's interpretation of non-significant results. Because the doctrine that we teach in the statisticians teach, is that if you get a non-significant result doing a statistical test, that means no evidence. And we thought everybody understood that. That non-significant means no evidence. But they claim that they looked at
Well, they claim it comes up in medicine and certain fields like, I guess, epidemiology or stuff like that. I don't know. I've never seen it, but does this happen
In psychology, misinterpreting the p-values and the null outcomes.
But as saying that it proves that the null hypothesis is true or something like
Oh,
that.
no. Like I've never seen a paper saying that, oh, we didn't find a significant result, therefore the null is true. I didn't see any cases
I don't
of
think
that.
they would explicitly say that, but it's very easy for them to jump on the conclusion, oh, this drug is not toxic, because there's no evidence that it is toxic.
They claim that in the papers they surveyed, 30% of the cases people said. Right? That's what
Is it unreasonable to say that it's evidence that the null hypothesis is true? Some evidence for it, and no evidence that there's a cause other than a random effective measurement.
What we teach in statistics courses is that there's no evidence. Because it might just mean your
Well,
sample.
obviously you've got evidence, the experiment got results.
You know, the sample size might be so small that.
So a teeny bit of evidence.
Uh,
I'm sorry to quibble, I just want to learn how to speak the language.
I mean, I think that there's people who would say that it's not evidence at all. And I would say that, I would agree with that it's not evidence at
There's
all.
no evidence at all.
I would say no.
That's, I think, kind of the doctrine we try to teach in statistics.
I mean, I can see that you might teach that to people who are consumers who don't want to have them think very much. But why
But
did you say that?
Well, you have to think, if you think about how the whole thing's set up, I mean, you make assumptions, and then all you calculate is that if your assumptions were true, that the thing that you observed isn't unlikely. But I mean,
Well, you can actually have a likelihood. How likely is it that you get this result on the null hypothesis? How likely is it that you get it on an alternative hypothesis? As long as there's a difference between those two, it'll be evident.
well, I guess this might make sense. I mean, maybe in a Bayesian setting, you can do this kind of thing.
Yeah, I mean,
Yeah.
I mean, that's
Okay,
how,
okay,
to
let
the
me
extent I
add something,
understand this
let me add
discussion,
something to what
I
you,
think naively,
A high-
the Bayesian looks at this and they think, of course they got it themselves all tongue-tied.
well, I don't think I think if you look more closely at this, you would revise what you want to say, Barry, because
That's probably right.
because a high p-value does not imply that the likelihood is greater under the,
No, I wouldn't say anything about p-values.
we're talking about p-values.
What?
We're talking about p-values. People are interpreting high p-values as evidence for the null hypothesis. That's what we're talking about.
So just the claim that you got a high p-value is evidence, not the results of the experiment itself.
They aren't doing any other analysis of the experiment. They're using the high p-value. That's right.
Yeah, that may just obscure what evidence you got. There'd be
Whatever,
an
you know.
objection to p-values.
Whatever. So Bayesians and non-Bayesians among the statisticians are saying, no, you shouldn't do that. But practitioners, according to this
I'm
article,
not disagreeing with that. I know
these practitioners are doing it, according to the writers in. And I must say that we have a journal, a magazine, that statisticians get. I get it in hard copy still, with the name Significance. I don't know if Harry and...
I do.
Like an advertising.
No, it's a kind of trade, it's a little magazine.
I mean, they
It's
chose the title to have as a promotional.
Yeah. So it is sponsored, that magazine is sponsored jointly by the Journal of the Americans, by the American Statistical Association and the Royal Statistical Society. And it publishes success stories of statistics, right? That's
I've
basically-
never read it.
You never read it?
There are interesting things in there.
There are things that might be useful for teaching.
Yeah.
They kind of promote the discipline, but I think it goes to believers, some people that already believe in statistics. Harry is enough of a skeptic, he doesn't even read it, right? But I get it. Anyway, their reaction, of course, to this editorial or commentary in Science magazine was, God, what do we do now? And, but in the issue in which they reacted to this, they published an article by a statistician in an accounting department, like me. I'm a statistician in an accounting department. And there was a statistician in an accounting department in Texas, University of Texas at Dallas, which is a top business school. University of Texas at Dallas now, they got the best researchers. So this guy had done a study, he and his students had done a study, and I have confidence in what he did. He did a study of our leading journal in accounting research. It's called the Journal of Accounting. It's called Accounting Review, excuse me, Accounting Review. We've got the Journal of Finance and Accounting Review. He surveyed the articles in Accounting Review, and he found out that this same sin is very common. Not only that, there was one example that the journal itself pulled out and promoted as the best research of the year. That showed that, claiming to show that some new accounting rule had no effect. Because there was a high p-value. You know, well, this is not the only thing wrong with statistics and accounting research, I'll tell you. I mean, it's much worse off than psychology. So, you know, yes?
I'm sorry if this is a very low-level question, but I'm trying to think about this. So, can one say that having a high p-value is evidence against the alternative? Does that work? Or would that be misleading as well?
Let me show you some examples. So now we're getting into what I would like to do.
I think it depends on the power. I think it depends on the power of the test to answer this
Power.
question, right?
Power.
Oh.
So the one thing that was new in the 20th century was the concept of power. And that didn't come from Fisher, that came from Neyman. from Neyman and Pearson. In 1933, they said, to have a good test, it should have a high probability, if you're going to have an all or nothing test, accept or reject. Okay, you can set the significance level at 5%. That's the probability of rejecting wrongly. But you also should have a high probability of rejecting when you should reject. When the alternative hypothesis is true, you should reject with high probability, and that means power. So 1 minus the power is the type 2 error. So you want to, in addition to a small type 1 error, you want a small type 2 error, and you want a high power. So in our elementary stat classes, I think, we drum this into the students. Type 1, type 2 error, power, and then in many fields they go out and you never hear about power again. The PhD students in my accounting department, in my business school, the PhD students in finance and accounting have never heard of power. Or they forgot about it. Some stat teacher may have taught about it, but you never see it mentioned in their articles. Out the window. That is sort of one level of incompetence when power isn't even mentioned. But there's another level of confusion. And a lot of the critics, leave aside these people that wrote the Nature editorial, but a lot of other people have been complaining about practice, and this is especially true in psychology, have complained that there's a lot of confusion from mixing up Fisher and Neyman. And I think the core, where I see some core of validity to that complaint is that you get trouble when you mix up p-values with power. Those ideas don't fit together, p-values and power. And I want to show some examples of what goes wrong when you try to mix p-values with power. So I have one example here, but I think actually I'll do better with my second example. I want to give an example of a p-value that has, a test that has a 5% significance level, a very high power, and a borderline outcome. So we'll look at the borderline. So we could make the example that you just barely reject or you just barely accept. We're going to work right at 5%. So I'm going to make it reject. Okay, so what is it? The null hypothesis is that y is normal with mean 0 and standard deviation 10. The alternative hypothesis, call that Q, is that y is normal with mean 37 and standard deviation 10. So null hypothesis 0, alternative hypothesis 37. The standard deviation is 10 in either case. Okay? And so what is right in between? Well, not exactly in between, but we're going to observe 16.5. So 16.5 is pretty high for mean 0. And it's pretty low for mean 37. Okay, now it's high enough for mean 0 that you're going to reject at 5%. The probability of being bigger than 16.5, probably the p-value, the probability of being bigger than what you actually observe, the p-value is less than 5%. So if you're using a 5% test, you're going to reject. So statistician A doesn't do accept reject, he just calculates a p-value. Statistician B uses a 5% test, she rejects. Statistician C does what I'm advocating, which is she makes a bet. Statistician, now the betting idea, not everybody heard that. Barry and the group that have been coming to the seminar regularly have heard it, but there's 3 of you who have not heard my betting story. So let me tell my betting story very briefly. My idea is the way you should test a hypothesis is that you should buy a payoff at the price the hypothesis gives. So the null hypothesis gives expected values to payoffs. So buy a non-negative payoff that costs $1. That's my idea. And see if you can multiply your money. So if the payoff is non-negative, you're only risking the dollar you pay. You pay $1, get a non-negative payoff, and if your payoff is 100, you multiply your money by 100. And you shouldn't multiply your. That's all. It's like I'm saying. It's like put your money where I'm saying to the null hypothesis. Put your money where your mouth is. If you really think these are the right expected values, sell me one. And if I make a lot of money off of you, I multiply my money by a lot, I have very good grounds for saying you didn't do a very good job. Your hypothesis is not very good. If we think that probability is basically about betting, there's no better evidence I could have against a hypothesis than that. You said those were the probabilities. I gambled at those probabilities. I beat you badly. I multiplied the money I risked by a large factor. And the larger the factor, the stronger my evidence against you. So the p-value is a graduated measure of the evidence. The smaller the p-value, the more the evidence against the hypothesis. I'm doing it the other way around. The bigger I multiply my money, the more the evidence against the null hypothesis. So I get a graduated measure of the evidence against the hypothesis by betting against it. And in my story, in my spiel, in my account, what I am doing is simpler than a p-value. A p-value is very complicated. A p-value is not about one bet. A p-value is about a whole family of bets. A significance test with a fixed significance level, if you bet at the 5% level, okay, you could say that's like trying to multiply your money by 20. That's one bet. But the p-value says, okay, could I multiply my money by 20? Yeah. Could I multiply my money by 50? Could I multiply my money by 100? You're looking at all the possible ways you could have multiplied your money if you had known how to bet. So you're looking at a whole family of bets in order to get your number, the p-value. But I'm only looking at one bet. But the difference is my bet is not all or nothing. I'm not just betting at trying to multiply my money by 20 or lose it all. I'm doing a graduated bet. I'm buying a payoff for its expected value, and that payoff could have all kinds of different values. And it turns out that when I buy a payoff, it turns out mathematically that when I do that, when I buy a non-negative payoff for its expected value, it turns out that defines an alternative distribution. And the payoff I bought is the likelihood ratio with respect to that alternative distribution. That's just a little bit of math. Yeah.
So your approach conforms to the likelihood principle, right? It's how likely it is that the evidence on the two hypotheses carries the weight.
But I don't start with the alternative hypothesis. Exactly.
Where these other approaches don't.
It conforms in the sense that my bet defines the alternative.
So it seemed to me, I think I didn't really fully understand your account, and I didn't make the effort to do it. But it seemed to me when I heard you talk before, I was saying, Glenn has an account that's taking a step in the direction of being a Bayesian. Good. From my very naive, simple thing, the way I was thought.
Okay, that's fine. But I'm not starting with the alternative. I'm defining an alternative.
No, I see that. Right.
And that means that I might not have an idea about an alternative. I might be completely clueless. I could just say, well, I got a bet, I'll do this.
So that's an interesting difference because they might, the problem with Bayesian is that you're artificial about what the alternative is.
Yeah. So that's my idea of a bet. So yeah.
So just to clarify that, you don't require this implied alternative, which I guess is Q or maybe P or
It's
Q.
Q.
doesn't need to be a probability distribution, does it?
It is. Mathematically, it is. In the case where if I start with a, yes, it is.
Well, what do you start, what are you specifying?
If I'm specifying a probability, that's the math I did. I don't have that, I don't have it on the slide right now, but in the slides I used before, I did that little bit of math. I start with a probability distribution.
Mm-hmm.
Let's suppose it's discrete. So that being a probability distribution means that when I add up over the different possible values, it's 1. That's what I start with. I'm testing. I can make it more complicated, but in the simple case, my null hypothesis is a probability distribution. Now, I make a bet. Let's say my bet is a function of y that is non-negative, and its expected value is 1.
Okay, never mind. So you're assuming it has an expected value?
Yeah.
Yeah, okay.
I choose a non-negative, that's right, because I only have $1 to pay. I'm assuming that when when the null hypothesis says these are the probabilities, I'm assuming it's offering me all non-negative payoffs at their expected value. Some expected values might be infinite, but it's not going to do me any good to pay an infinite amount.
Well, I mean, in terms of, I guess I would wonder why that is necessary, that assumption that the expected value is 1. You might be paying, you can say I have to pay $1 for this bet, but why does that mean the expected value of the bet?
I want to see how much I can multiply my money.
But what's the expected value have to do with any of that? Because you've specified what S is, right? Which is how much you get paid if Y happens.
And I have to know how much should I pay for that.
No, you have to pay $1.
Yeah, because the expected value is $1. It doesn't matter.
I'm just trying to make this. No, I don't. I'm not worried about what's on the right. I'm worried what's on the left.
Why the expected value?
In other words, sure, it might be the expected value, but that's not necessary to make a bet for $1. I don't have to do a calculation to agree to make a bet with you for $1. And I don't need to make that calculation.
Are you a null hypothesis? I'm betting against the null hypothesis, which is a probability distribution.
Yeah.
So the probability distribution, I'm saying that the meaning that I attach to that probability distribution is that it is offering me any payoff I want to buy at the expected value of that payoff. That's the interpretation I'm giving to it.
The expected value of the payoff. Oh, that's under the P.
Yeah.
Oh, okay. I thought it was.
I should put a subscript P here.
Oh, okay.
The expected value under P of the payoff should be $1. It doesn't have to be $1, it can be $2. But I'm interested in how much I multiply.
No, that's fine.
So
I thought it was under
I may as
Q.
well normalize it and make it $1. Okay, then how do I get the Q out of that? Well, what does this formula mean? This formula means that the sum over y of S of y times P of y is 1. The expected value being 1 means that if I multiply the values times their probabilities, it adds up to 1. But S is non-negative and P is non-negative. That means the product S times P is a probability distribution. I call it Q. Q is equal to S times P. That means S is equal to P divided by Q. And my payoff, S of y, is P of y over Q of y. That's the likelihood ratio. So when I buy a non-negative payoff for price 1, I am buying a likelihood ratio. It's just math, right? So that's the way I bet, and I try to multiply my money. So that is my alternative. So these two statisticians are doing their thing. I'm the third statistician, and I test by betting. Now let's talk about power. Let's talk about power. this test that rejects, remember what we were, the test rejects, the Neyman-Pearson test rejects when y is bigger than 16.445. That's the 5% level. What is its power? Its power under Q is the probability. Q, remember, has mean 37. So what is the probability if you have mean 37? What is the probability of being bigger than 16.5? 37 is 20.5 away from 16.5. That's more than 2 standard deviations. This is a one-sided test. So the probability of being more than 2 standard deviations below is only 2%. So the power of this test is 98%. So this is a 5% test with power 98%. And it rejects. Who could ask for more? By the conventional theory, you have a 5% test with high power, it rejects. That's evidence against null hypothesis. If you look at the likelihood ratio, that's not true. If you look at the likelihood ratio, I mean, I don't have to do the formula here because it's pretty obvious. The thing is closer, the 16.5 is closer to the null hypothesis than it is to the alternative hypothesis. You know, the type 2 error probability is smaller than the type 1 error probability. So, you know, so you have this problem. The power is too big. The power is too big. This is the confusing thing about power. When the power is too big, you reject even though the null hypothesis is favored. And that comes out of my betting approach because so the point, so one way of describing this is the idea of power does not play well with p-values. The p-value has got one message, reject. When you say, okay, the thing has good power and good p-value, p-value and power are kind of from 2 different worlds. P-value is, you know, the Neyman-Pearson procedure is don't look at the p-value, just stick with 5%. Don't calculate the p-value, just to make your 5% level reject if it's like, reject if you're in the rejection region, don't talk about p-value. So the power really belongs to that world where you're talking about type 1, 2, type 2 error, and you're not talking about p-value. You put together p-value with power, you've got a mess. Because it's not so simple. It's not true that high power and low p-value is evidence against the null hypothesis. It's not true. When you look at the example, you wouldn't do that. So my theory of betting, my betting theory, has an alternative to power. And the alternative to power is what I call the implied target. So the implied target, what is the implied target? The implied target is the exponent of the expected value under Q of the logarithm of the payoff. The payoff is non-negative, so the logarithm is something, so you can take its logarithm. If I take a logarithm, then after I take the expected value, I want to take the exponent to get back to the same scale. If you think Q is true, if you take your alternative seriously, and you think that Q is true, this is the score that you're aiming for. You think that it's on a log scale. Why do I do a log scale? And I give an argument for why I would want to use a log scale. The log scale is because I'm doing science, and I think this is not the only test that I or someone else might do. Somebody else might come along and do another test. And when they came along and do another test, what they should do is they should take the money I made from my test and invest it in their test, so that you can opportunistically continue betting and build up your capital. And in fields where people do this, they use this logarithm. They maximize the expected value of the logarithm in order to maximize the rate of growth of the capital. So people use this idea in information theory and machine learning and finance, and I'm saying we should use it in statistics. So this is my implied target, and I say the test should not even be done. You shouldn't do this test. I mean, the conventional theory is you shouldn't do the test unless it has high power. My theory is you shouldn't do the test unless it has high implied target. If it doesn't have a high implied target, you shouldn't do it. Yeah.
Do you bet on a single Y or a subset of Ys that is for you to choose?
My bet has different payoffs for different lines.
I know, but suppose, what if I bet on the set of Y being 1, 2, 3, and so it just so happens to decide those are the most highly, because
I got a message that I have to
for
go
every
home.
Y,
so-
you
You
pay
make a bet, all or nothing bet. You can do that.
Well, you
That's
pay
a
so,
Neyman Pearson bet. That's the usual bet.
I don't think I meant that. I was thinking of something like, well, suppose that you are, like Y would be that, where that, I guess, the location of the true meaning that this observation Y should come from.
Tell me
Suppose it is
what
the
bet
same.
are you thinking about?
I'm thinking, so suppose that I am somebody who's trying to learn the location, the true location of this observation that is coming.
Are you
Right,
gonna
so-
bet against the null hypothesis?
The null is, say that it's.
0, 10.
Yeah, 0, 10, okay.
Are you gonna bet against 0, 10?
I would like to bet against 0, 10.
Okay. How are you gonna do it?
I was gonna ask, because what is the bet, you put down $1 for what claim? What is the claim that would
Any
make you
payoff,
win?
any payoff. So it could be a 0, 1 payoff. It could be that if you're in this set, I get 1, I get some number, 1 over alpha. And if I'm not in that set, I get 0. So if P gives 1 over alpha, gives probability alpha to that set,
Mhm.
I can make a bet that gives me 1 over alpha if it's in that set, and 0 otherwise.
So that is to say that you chose S as a function that looked like that.
Yeah. So S can be any function, that function has expected value 1.
But in that particular case, that you chose S to be that step function, that,
Yeah, yeah. So a Neyman-Pearson bet, a Neyman-Pearson test is that kind of bet. But I'm interested in other bets that are not just two-valued, all or nothing. I'm interested in bets that don't just give me 1 over alpha or 0. They might give me 5, they might give me a half, they might give me, in this case, my bet. Well, the bet is always a likelihood ratio, so it can be anything between 0 and infinity. And in this example, the payoff of my bet turned out to be 0.477. What does that mean? I paid $1 and I got 48 cents back. So that is not evidence against the null hypothesis. I bet against the null hypothesis by paying $1 and getting 48 cents back. No, that's not evidence against the null hypothesis. And that's what the likelihood ratio says. The likelihood ratio says the null hypothesis is more likely than the alternative. And that is reflected by the fact that I only got 48 cents back. Whereas the Neyman-Pearson test just rejects. Now the Neyman-Pearson test was a all or nothing test. And it made, how much did it make? It made $20. It was a 5% test, alpha is 5%, so it paid off $20. And I'm saying this is not a very good test to make, because what is the likelihood ratio implied by that test? The likelihood ratio implied by that test says that the probability of the alternative hypothesis implied by this. Remember, what is the alternative hypothesis? You take the bet and you multiply P by it. And everything outside that rejection region is 0. So the alternative hypothesis when you do a Neyman-Pearson bet is that everything outside your rejection region has probability 0. That's the alternative hypothesis. You don't take that seriously. You could use that alternative hypothesis and your bet might be lucky and hey, you multiplied your money by 20. But it's a ridiculous alternative. That's where I'm going. So the point of this is Now, in this particular case, what is the implied target? I can do the calculation for the implied target, and it's 939. So this test is a good test because it has a high implied target. Well, to be a good test, I would put down two requirements. One is the alternative has to be plausible. In this case, the alternative was already announced. It was 37, 0. So this doesn't make any sense unless that's a reasonable alternative. Somebody says, yeah, the null hypothesis is 0, but it could be as much as 37, so I'm going to test 37. If 37 is ridiculous, nobody thinks it could possibly be 37, it's not a good test. But if the alternative is something reasonable, and if the implied target is high, it's a good test to make. And when you have a good test to make that has a high implied target, and it comes out you're going to lose some of your money, it's clearly evidence for the null hypothesis. So in this case, it is evidence for the null hypothesis. So my point is, betting, the betting score and the implied target play well together. The p-value and power do not play well together. And I think, you know, so I'll come back to what I was saying. I think the kernel of truth in what my colleagues are complaining about the mixing of, Gigerenzer does this. You know Gigerenzer, the name Gigerenzer? Yeah, so well-known psychologist who writes lots about statistics, and for some 40 years, he has been complaining that the statistics textbooks in psychology, but also not in psychology, the statistics textbooks are making a mess because they're mixing p-values. They're mixing what he thinks is Fisher with what he thinks is Neyman Pearson. So you should only teach one of those guys because they've got different theories. I think the kernel of truth in what he's saying there is that p-value and power don't play well together. And I'm arguing that my betting theory, I have my betting score, which replaces p-value, and my implied target, which replaces power, do play well together. They give a coherent story. No matter how things come out, it's a coherent story. The implied target is high, and I got a high betting score, bad for the null hypothesis. The implied target is low, don't do the study. The implied target is high, but the p-value, the betting score comes out low. You did a good test, and the null hypothesis passed it, and it's evidence for the null hypothesis. So we don't have this issue where our evidence measure comes out. We don't have this issue of no evidence. There's always an answer. There's always an answer. If the implied target is middling, I mean, you do have this situation. Here's a case where I changed it to where the null hypothesis is 0 and the alternative is 20. And the p-value, we observed 5. So what's the probability of getting more than 5 when the null hypothesis is 0 and a standard deviation of 10? Well, that's only half a standard deviation away from 0. The probability of being half a standard deviation or more above 0 is about 30%. So this is a high p-value. By p-value, it's no evidence against the null hypothesis. Statistician B does a 5% test. So he only rejects if you're bigger than 16. You're only 5, he doesn't reject. If he thought that it was a bet, he would be losing his money. What is the power? The power is 64%. This is a test that has 64% power, 5% significance level, and it does not reject. Is that evidence for the null hypothesis? Well, given the previous example, it's very hard to say whether you want to consider this evidence for the null hypothesis. But the bet gives an answer. The bet has target 7. Implied target is 7.39. Not like the implied target. The previous example, the implied target was 939. Excellent test. Very strong test. This is okay. I mean, if you multiply your money by 7, that would be impressive, multiply your money by 7, but it's not the end of the world. What actually happened? The payoff is 0.36. I lost 2/3 of my money. So does that favor the null hypothesis? Yeah, mildly favors the null hypothesis. When I did a bet I did a study that had some relatively good implied target, but actually it came out in favor of the null hypothesis. How much it favors the null hypothesis is, it could, I could multiply, I could lose 2/3 of my money pretty easily, but it still favors the null hypothesis a little bit. So there's no harm in saying it favors the null hypothesis a little bit. So I think it's a more coherent story with implied target and betting score. That's my story. So I started out saying I wanted you guys to ask me questions, but I didn't let you ask too many.
Well, we can maybe take a couple minutes for questions,
Oh, I don't have
especially for people who aren't here that often.
No, these are like way above my head.
Oh, I'm sorry.
No. I'm glad to learn anything by coming here.
Oh, well, thank you for coming.
Actually, I came to one of your talks. It was in the philosophy's 5th floor,
Mhm.
and betting sounds like very similar, but I don't remember the exact details, so I couldn't follow up. I couldn't bridge any links or find the similarities between your talk and this betting idea.
Well, there are some similar ideas, I guess, but this is I wasn't really given much of a statistical proposition there. I was more or less just, I was actually talking about betting. I think Glenn actually doesn't think it's important for people to risk money on these things. He just thinks it's a language that I guess in one sense you think helps people understand, because people have a better intuition for it.
I understand.
Yeah.
Okay.
But the next week's talk will also be on the replication crisis as well. So,
What is that?
Correspondence.
Oh, it's not
and I don't know the title, but I'll send it to Lee. And
That's how I got the
Yeah.
first one. Thank you very much.
Okay, thank you.
When you don't have the alternative, do you just Q be the maximum likelihood estimate?
No, when I don't have an alternative, I don't, see, I'm supposed to make my bet before I see the evidence. Just like Naaman Pearson wants to make a bet before you see any estimate. So the bet is only legitimate if you do it beforehand. So if I don't
The
have
most
a,
powerful test is the one that gives the likelihood ratio, and then you're supposed to put on top the MLE and gives you the maximum likelihood. You don't do any.
no, the idea is, I have to make my bet before I see why. The point is that I can make my bet on a whim.
But then, okay, so do you then make the bet after seeing the data?
No. I make my bet before I see the data. Otherwise, it's not a test.
But so how
I
am I
mean,
gonna
Naaman
even
Pearson-
have I either derive, how do I do, because I can't just come up with something and make sure that I can do well, right?
No.
that's why it's a test. Right?
You're testing. Now, I've got a second, the paper has a part 2 about estimation.
I'm trying to wrap my head around why the likelihood ratio test utilizes the MLE, which is a function of the data.
Oh,
And
you're
it gives
talking
me
about,
consistency.
you're talking,
Like, it
okay.
gives me validity.
Okay, so I'm testing, okay, so basically, so you're talking about composite alternative, or composite null.
Yeah.
Okay, so I would talk about that after I talk about estimation. So this theory has, so my paper, I've only talked in my talks, I never get past part 1, which is testing a simple null. So testing a simple null, even if you think the alternative is composite, your bet defines a specific alternative.
Mm-hmm.
It might, you might think, oh, if you're a Bayesian or something, you might think, oh, that's averaging over a composite alternative. But the bet itself defines a specific alternative, and that is the alternative that my bet that my the alternative is is defined, as I explained here, is defined by the bet, and it's sort of the it's what my bet is optimal against. I have to choose a bet. I gotta choose. I choose a bet. Maybe it's out of a whim. I say, oh, I'll try this today. Tomorrow I'll try something else. I don't know what I'm doing, but all I can do is bet. But the bet itself defines an alternative, and then the implied target is how well you should do under that alternative. Your bet is optimal for that alternative, and if it doesn't even do well under what it's optimal for, it's not worthwhile. That's how you evaluate whether the study is any good. If the alternative is also ridiculous, then the study is not worthwhile. So you decide on a bet. If the alternative is reasonable, and if the implied target is good, then the study is good. Maybe the study should be published no matter how it comes out. But if one of those conditions is not satisfied, if the alternative is not reasonable or the implied target does not amount to anything, then the paper should not be published no matter how it comes out. If you have a high betting score, it'll just be because you're lucky because you didn't have a good implied target. So it's a way of evaluating. It allows you to evaluate the study before it's done, before you see the data. Now, when you want to do estimation, I mean, I think talking about composite nulls or something like that, it's better to talk first about estimation. So I want to get something like a confidence interval. Can I do that? Of course. I can do, a confidence interval, the way we teach it nowadays, is all the parameter values that survive a bet, that survive a Neyman-Pearson test. Well, I can say, okay, my warranty interval will be all the values that don't multiply my money by 5, or all the values that don't multiply my money by 20. So I have I have a bet. I specify a bet against each of the parameter values, and the ones that pass the bet is my warranty interval. Now the interesting thing about that is, our colleagues in the stat department are make a big deal out of nested confidence intervals.
Yeah.
I get them for free because I have my bets give graduated results.
But hold on, what are these sequence of bets? Because they are going to be sequence of cues.
No, I don't have a sequence of bets.
Well, just a collection for every.
For every no, I make a bet.
But then, so for every, I can index all of your bets, and those are just going to be a whole bunch of cues indexed.
For every no, there's a bet.
So that's
for every value of theta, there's a bet.
Which is a function. So in what
Yeah,
sense?
a function of theta. So I have a bet that's a function of theta.
Yeah.
Okay, now. That's why in the second part of my paper, I go a little bit more into the formality of my book with Pfaff. Because because how is this betting happening if you're giving a different bet for each parameter value? So I say, okay, we got a game. This game, the statistician is not in the game. But there's a player in the game that makes bets. And that's like it is in our book. There's a player in the game that makes bets. The statistician doesn't see it. The statistician is outside the game. But the skeptic in the game, the first thing that he learns is what theta is. The statistician doesn't. But the statistician tells the skeptic, gives the skeptic a strategy. And the strategy says, if theta is 2, bet this way. If theta is 5, bet this way. If theta is a half, bet this way. So the statistician tells the skeptic what to do. He knows what the skeptic is going to do, but he doesn't see him do it because he doesn't see theta. So after he sees y, after the statistician sees y, he thinks, well, if theta was 3, skeptic has multiplied his money by 100. But if theta was 2, skeptic has only multiplied his money by 3. So I can form an interval of all the theta values where skeptic didn't multiply his money by 100. That's like a 99% confidence interval. But I call it a 100-to-1 warranty interval. I can also, at the same time, I get an interval where skeptic has not multiplied his money by 20. That's like a 95%. And I get all those intervals nested for free. out of my one strategy for skeptic. I don't have to worry about whether my confidence intervals are really nested. I don't have to worry about their interpretation. It's all this betting interpretation. Comes for free. So I get nested confidence intervals out of this. And from that, if you want to do, you can do composite. You can talk about composite hypotheses and tests against, you know, and you can kind of talk about that language if you want, but you can get the intervals. So the advantage of this is, so, you know, Harry allowed one question and I went up 5 minutes over.
Well, I mean, I think that we can probably wrap it up and continue this if we're all,
Yeah.
you know, afterwards. So
Yeah.
thanks a lot.
Thank you
All
for
right,
listening
thanks.
to me again.